好, good afternoon, Professor and ladies and gentlemen. Today I'm going to present a journal article called the title is Towards Development of LED-based Time Domain Near Infrared Spectroscopy System for Delineating Breast Cancer from Adjacent Normal Tissue. And I'm Zhuang Qixiang. My supervisor is Song Kongbin. And this article is from IEEE Sensors Journal in 2021. And breast cancer in Taiwan is ranked first in women and accounts for about 12% of commonly diagnosed cancer cases around the world. And current um, current ways to diagnose cancer depends on uses the histopathology technique, which which need to which doctors need to take a biopsy from the patients and slice it into the micrometer thick tissue and do a manual inspection under a microscope. And the evaluation process usually takes days, so the patients cannot get immediate results from the examination. And this article's conclusion is that it utilizes a time domain near infrared spectroscopy system to achieve delineation between cancers and adjacent normal tissues. And the special part of the time domain nears they use is that they use LED light source rather than laser. So it's safer and more affordable and portable. And the measurement time is only 2 minutes. So it can be faster than manual inspection. And the system is uh, 10 times less expensive than existing commercial system. And the technique used in the study is the time domain NIRS, which is time domain near infrared spectroscopy. And it, it consists of a light source which can emit light pulse. Um, like the right figure, the light pulse is indicated by the green curve, and you can see the pulse width is about 0.2 microseconds, and and then the system also has a detector to detect the arriving photons distribution, like the right figure, the other two colors of the curve indicate the detected signal. And so the system can detect the temporal point spread function, which is these two curves, and then it's a non-contact detection system. And the time domain nearest is the highest resolution and accuracy within all the other nearest modalities. So the author used this technique. And and the the research used quantified three optical parameters to be optical biomarkers for cancer diagnosis. And the three optical biomarkers they found is effective attenuation coefficient and time of flight of photons and detected peak voltage. Uh, and Why the three parameters can distinguish between cancer and adjacent normal tissues, because uh, the two types of tissues differs in collagen and lipid content. So the the difference in this structural difference leads to this uh, difference in these biomarkers, and we can see that we will define the time of flight of photons to be the input pulse and the detected signals, the time between them. And the system is a time domain system is their self-assembled system, and which incorporate two components. And first is the optical component, which features two LED wavelengths, and they can switch between these two wavelengths, and also electronic modules featuring a fast switching LED driver and a photodiode to detect the transient intensity at the detector. And the system's schematics is like the figure, and uh, inside the systems there is a LED on the top of the system, and the tissues is placed here in the middle, and the detector is in the bottom. So the system is a transmission-based spectroscopy system. And the sample size here is about 1 millimeter thick. And the total system is pretty small. So its height only 6 centimeter and its diameter is 5 centimeter. And the Beer-Lambda laws is used in this article to quantify tissue absorption and scattering. And like this formula here, uh, the I naught means the detected intensity, and the V is voltage, detected voltage, and the voltage uh, V naught and V is difference between them is the whether there is samples between the in between the detector and the light source, and the there they calculate the effective attenuation coefficient by this formula by uh, plugging in the voltage they detect, and the result is that the detected peak voltage and the time of flight and this coefficient shows significant difference between two tissues. So the we can see that the normal tissues and cancer tissues differ significantly in these three parameters, and the reason why the voltage decreases and in the cancer tissue and the time of flight increases in cancer tissues is because an increase in collagen fibers in cancer tissues uh, uh, causing the light to attenuate more, and the time to be detected is longer. And due to the scattering in the cancer tissues, the effective attenuation coefficient is also higher. This